1943. Syracuse, New York. In a machine shop thick with metal shavings and grinding sparks, a machinist reaches for a chisel forged with steel that European metallurgists had declared chemically impossible for tool applications. The cutting edge gleams with molecular precision that defied everything Sheffield steel masters said American manufacturing could achieve. 80 years later, that same chisel still slices through hardwood with surgical sharpness. Meanwhile, modern chisels bought last month already show chips and dulling that render them nearly useless. The Europeans had dismissed American electric furnace technology as metallurgically unsound and commercially naive. Yet somewhere between those crushing expert predictions and today's disappointing tool performance lies a revolution that time forgot. One man's impossible gamble against 130 years of proven crucible steel tradition created tools that outlasted generations. But the secret died with the methods that forged them. The merger documents bore the date March 15, 1902, and Charles Herbert Halcom studied them with the methodical precision that had earned him respect among Syracuse's steel men. 13 Crucible Steel Companies, scattered across Pennsylvania and New York, would now operate under a single corporate umbrella, the Crucible Steel Company of America. On paper, the consolidation created the largest tool steel producer in the United States. In reality, Halcom knew it merely organized American defeat under one letterhead. Across the Atlantic, Sheffield steel masters read the American merger news with polite amusement. The Sanderson brothers, whose family had perfected crucible steel methods since 1776, exchanged correspondence with London colleagues about the colonial ambitions of American metallurgy. Their dismissal carried the weight of 126 years of uninterrupted market dominance. English crucible steel set global quality standards because English methods worked with mathematical precision that Americans had never matched. Halcom understood those methods intimately. Born into Sheffield steel aristocracy, he had apprenticed in the Sanderson brothers' workshops, learning to read furnace temperatures by flame color and judge steel quality by spark patterns. At age 22, he had crossed the Atlantic to manage Sanderson brothers' Syracuse operations, bringing English expertise to American soil. 21 years later, he served as president of the newly consolidated Crucible Steel Company, commanding 13 facilities and 3,000 workers. Yet every ton of steel they produced reminded him of American inferiority. The Sheffield process had achieved perfection through centuries of refinement. 30 graphite crucibles, each charged with 60 to 100 pounds of carefully selected iron and precisely measured alloy additions, heated simultaneously and coal-fired. Furnaces that reached 3,000 degrees Fahrenheit. The timing required absolute precision. 3 hours of controlled heating while furnace workers monitored temperature by eye, adjusting coal flow and air draft to maintain consistent heat across all 30 crucibles. When the steel reached liquid perfection, teams of workers wrapped in wool and burlap clothing, soaked in cold water for protection against radiant heat, hand-teamed the molten metal into ingot molds. The process demanded master craftsmen who understood metallurgy through generations of inherited knowledge. Sheffield steel achieved superior quality because Sheffield methods eliminated variables that plagued American attempts at duplication, each crucible heated independently, allowing precise temperature control impossible with larger furnaces. Hand teaming ensured proper pouring technique that prevented inclusion defects. Most critically, the small batch sizes, never exceeding 100 pounds per crucible, enabled metallurgists to monitor chemical composition with accuracy that larger heats could not match. American tool steel failed because Americans attempted shortcuts. Larger furnaces promised efficiency but sacrificed control. Mechanical handling replaced skilled hand teaming but introduced contamination. Cost-cutting measures that looked attractive on balance sheets produced steel that disappointed customers who demanded Sheffield quality. The London Iron and Coal Trade Review published detailed analyses proving why American methods would always produce inferior results. European metallurgists declared electric furnace steel chemically impossible for tool applications, citing fundamental principles of iron chemistry that Americans apparently ignored. Even Halcom's own board questioned his private fascination with Paul Héroule's electric arc furnace technology. The French inventor's process could theoretically reach 3,300 degrees Fahrenheit, 300 degrees hotter than crucible furnaces, while melting 2,000 pounds at once instead of 100-pound batches. The mathematics appeared compelling. One electric heat could equal 20 crucible batches. But mathematics meant nothing without practical application, and no American company had successfully scaled electric arc technology for tool steel production. The engineering challenges seemed insurmountable. American electrical infrastructure in 1902 barely supported city lighting systems, much less industrial furnaces requiring massive power loads. The nearest generating station produced intermittent power that fluctuated with weather conditions and competing demand. Syracuse's electrical grid could not reliably deliver the consistent current that electric arc furnaces required for stable operation. Even if power problems could be solved, no American metallurgist understood electric arc chemistry well enough to control steel composition during the violent electrical heating process. Halcom spent evenings in his home study, sketching furnace designs on engineering paper, while calculating power requirements that exceeded anything attempted in American industry. His wife Sarah watched him cover pages with electrical diagrams and metallurgical formulas, knowing that his obsession with electric furnace technology threatened everything they had built in Syracuse. He possessed detailed knowledge of crucible steel methods that guaranteed profitable operations, yet he risked that security pursuing French electrical experiments that European experts had declared commercially impossible. The truth that haunted Halcom's calculations was brutally simple. America would never compete with Sheffield using Sheffield's own methods. English steel masters controlled not only the technical knowledge, but also the skilled workforce, the supplier networks, and most importantly, the customer relationships built over more than a century of consistent quality. American crucible steel would always be judged as inferior imitation rather than legitimate competition. By December 1902, Halcom realized that his position as president of America's largest tool steel company had become a prison of inherited limitations. The board expected him to manage decline gracefully, maintaining market share through price competition rather than quality improvement. They viewed his electric furnace proposals as dangerous experimentation that risked company resources on unproven technology. When Halcom presented detailed plans for electric arc steel production, board members reminded him that crucible steel had prospered for decades using proven crucible methods. The final confrontation came during the March 1903 board meeting. Halcom presented 2 years of research demonstrating electric arc superiority, higher temperatures, larger batch sizes, better metallurgical control, and ultimately, superior steel quality. The board voted unanimously to reject his proposal, citing European expert opinions and potential customer reaction to abandoning traditional methods. They offered Halcom a choice: continue as president using established crucible technology or resign to pursue his electrical fantasies elsewhere. On March 27, 1903, Charles Herbert Halcom submitted his resignation as president of the Crucible Steel Company of America. The decision shocked Syracuse's industrial community and delighted Sheffield steel masters, who viewed his departure as confirmation that American metallurgy lacked serious leadership. What they did not anticipate was Halcom's next move: incorporating the Halcom Steel Company with $200,000 in capital, purchasing 40 acres of land directly adjacent to the Sanderson Brothers works, and beginning construction of America's first electric arc furnace designed specifically for tool steel production. The incorporation papers for Halcom Steel Company bore the signature of Charles Herbert Halcom on April 15, 1904, along with capitalization of $200,000, a sum that represented everything he had accumulated during 21 years in American steel production. His 40-acre site on West Fayette Street sat so close to the Sanderson Brothers works that employees from both facilities could wave to each other across the property line. Former colleagues at Crucible Steel watched through office windows as construction crews broke ground for what Syracuse newspapers called Halcom's Electric Experiment. The recruitment of metallurgists began immediately. John A. Matthews, Crucible's most respected chemist, resigned after Halcom offered him a 20% profit-sharing stake in the new company. 3 furnace superintendents followed, then the head of quality control, then the chief pattern maker. Each departure carried away decades of accumulated knowledge about American tool steel production, weakening Crucible while strengthening Halcom's venture. The defections created bitter feelings among Crucible's management, who accused Halcom of stealing proprietary expertise to benefit a competing enterprise. Working directly with Paul Hérould's American representatives, Halcom designed an electric arc furnace unlike anything operating in the United States. The specification called for 1,500-pound capacity, 15 times larger than typical crucible batches, with 3 carbon electrodes, each 8 inches in diameter, suspended above a refractory-lined steel shell. When energized, those electrodes would create electrical arcs reaching 3,300 degrees Fahrenheit, hot enough to melt steel faster and cleaner than any crucible method ever developed. The engineering challenge lay in controlling those violent electrical discharges with sufficient precision to produce consistent tool steel chemistry. The power requirements staggered local electrical engineers. Halcom's furnace demanded 1,000 kilowatts of continuous electrical supply, more electricity than most entire factories consumed. Syracuse's municipal power grid operated intermittently, providing lighting for downtown businesses and residential neighborhoods, but lacking the capacity or reliability for heavy industrial applications. The nearest generating station produced fluctuating current that varied with weather conditions, seasonal demand, and mechanical breakdowns that interrupted service without warning. Negotiations with Niagara Mohawk Power Corporation consumed 6 months and $45,000, nearly 1/4 of Halcom's total capitalization. The solution required dedicated transmission lines connecting Syracuse directly to Niagara's hydroelectric generating station 25 miles away. Construction crews spent the summer of 1904 laying heavy copper cables through Syracuse streets, installing transformers capable of handling industrial electrical loads, and building switching equipment that could route power exclusively to Halcom steel during furnace operations. Local newspapers dubbed the project Halcom's Folly, questioning whether electric steel production justified such massive infrastructure investment. The furnace construction revealed engineering complexities that crucible methods had avoided through centuries of development. Refractory bricks lining the furnace interior had to withstand 3,300-degree temperatures while maintaining structural integrity during repeated heating and cooling cycles. Standard fire bricks failed catastrophically during initial tests, cracking from thermal shock and contaminating steel with silica inclusions. Halcom's engineers developed custom refractory formulations using high alumina clay and graphite additives, creating bricks that could survive electrical arc heating without chemical degradation. Electrode positioning systems demanded mechanical precision impossible with crucible technology. 3 carbon electrodes had to strike molten steel scrap simultaneously, creating stable electrical arcs while maintaining exact spacing throughout the melting process. Manual positioning produced inconsistent results and frequent electrode breakage. Halcom's team designed hydraulic positioning mechanisms with gear-driven adjustments that could move electrodes in increments of 1/16 inch, enabling operators to maintain optimal arc length as electrodes consumed during heating. Power control mechanisms represented the most critical innovation. Electric arc furnaces generated enormous electrical loads that fluctuated wildly as electrodes made and broke contact with steel scrap. Those fluctuations could damage generating equipment or disrupt electrical service throughout Syracuse unless properly managed. Halcom collaborated with Westinghouse engineers to develop variable resistance controls that automatically adjusted current flow, maintaining stable arcs while protecting the electrical infrastructure that fed the furnace. The first test heat was scheduled for December 27, 1905. Matthews prepared the charge: 1,200 pounds of carefully selected steel scrap, with precise additions of carbon, manganese, chromium, and tungsten to achieve tool steel chemistry. The electrical crew positioned electrodes exactly 8 inches above the scrap pile, checked all power connections, and confirmed communication with Niagara Mohawk's generating station. At 3:47 in the afternoon, Halcom gave the signal to energize the electrodes. The initial arc strike produced a brilliant flash that illuminated the entire furnace building, followed by a sustained electrical discharge that melted steel scrap with violence that crucible methods could never match. The temperature climbed rapidly: 2,000 degrees within 10 minutes, 2,500 degrees after 20 minutes, 3,000 degrees after 30 minutes. At 45 minutes, chemical analysis confirmed complete melting with steel chemistry that matched Matthews's target composition exactly. The metallurgical results exceeded every prediction. Spectroscopic analysis revealed carbon content of exactly 1.0%, with manganese, chromium, and tungsten distributed uniformly throughout the entire heat. Inclusion counts. The microscopic impurities that weakened tool steel measured lower than the finest Sheffield Crucible steel ever tested at Watertown Arsenal. Most remarkably, the electric arc process had achieved superior homogeneity across the full 1,500-pound heat, while crucible batches typically showed chemical variations even within individual 100-pound crucibles. Chemical analysis proved superior metallurgy, but tool steel quality ultimately depended on cutting performance under actual working conditions. Matthews cast test bars from the first electric heat-treated them using conventional methods, and ground cutting edges according to standard specifications. The critical test would determine whether electrically melted steel could hold an edge like crucible steel or better. The first cutting test used hickory wood, the traditional standard for measuring tool steel performance. Halcom's electrically produced chisel sliced through hickory with sharpness that surprised even Matthews, maintaining its edge through cuts that would have dulled conventional tools. Comparison tests against Sheffield Crucible steel showed identical performance initially, but extended testing revealed the electric steel's superior edge retention over hundreds of cutting operations. By February 1906, Halcom steel had completed dozens of test heats, each confirming the electric arc process's metallurgical advantages. Production efficiency far exceeded crucible methods. 1,500 pounds melted in 90 minutes compared to 2,400 pounds requiring 8 hours in 30 crucible furnaces. More importantly, the electric process delivered consistent chemistry that crucible methods could not match, heat after heat after heat. John Matthews bent over his laboratory bench in March 1906, grinding steel samples from the latest electric heat while formulating what would become the most successful tool steel composition in American industrial history. The chemical analysis showed precise control that crucible methods had never achieved: 1% carbon for hardness, 1.2% manganese for strength, 0.5% chromium for wear resistance, and 0.5% tungsten for edge retention. Matthews named his creation ketose steel, derived from the Greek word for whale, massive, powerful, and built to last in the deepest industrial waters. The electric arc process enabled metallurgical control that transformed tool steel production from art to science. Crucible methods required master craftsmen to judge steel, chemistry by spark color, flame patterns, and decades of accumulated intuition. Electric furnaces allowed precise measurement and adjustment throughout the melting process. Matthews could sample molten steel every 15 minutes, analyze carbon and alloy content chemically, then add exact quantities of ferroalloys to achieve target compositions within tolerances of 0.05%. Production scheduling revealed the electric process's revolutionary efficiency. By April 1906, Halcom steel produced 2,000-pound heats every 90 minutes during normal operations. The mathematics compared favorably to crucible production. 30 80-pound crucibles heated simultaneously for 3 hours yielded 2,400 pounds every 8-hour shift. Halcom's single electric furnace produced equivalent tonnage in 3 hours with metallurgical consistency that 30 separate crucibles could never match. The quality measurements proved electric steel's superiority through rigorous testing protocols. Independent analysis at Watertown Arsenal compared ketose steel against the finest Sheffield Crucible steel using standardized hardness, toughness, and wear resistance tests. Rockwell hardness readings showed ketose steel achieved uniform 62 to 64 HRC across entire ingots, while crucible steel varied from 58 to 65 HRC within single batches. The electric process eliminated the chemical variations that plagued crucible methods, producing homogeneous steel that performed consistently regardless of ingot position or cooling rate. Edge retention testing revealed ketose steel's most remarkable characteristic. Cutting tools made from electric arc steel maintained sharp edges 40% longer than equivalent tools made from Sheffield Crucible steel. The superior performance resulted from controlled cooling that created fine, uniform carbide distribution throughout the steel matrix. Crucible steel showed irregular grain structures with coarse carbides that chipped under heavy use. Electric steel's rapid controlled cooling produced microscopic carbides that resisted wear while maintaining toughness. Major manufacturers responded to Keto Steel's proven performance with unprecedented order volumes. Pratt & Whitney, the precision machinery manufacturer, specified Keto Steel for cutting tools used in aircraft engine production. Brown & Sharp, America's leading machine tool company, ordered Keto Steel for measuring instruments, requiring dimensional stability and wear resistance. Cincinnati Milling Machine Company contracted for cutting tools that could machine-harden steel components without frequent resharpening. The order backlog reached 6 months by December 1906, forcing Halcom to expand production capacity. Construction began on a second electric furnace with 2,000-pound capacity, incorporating improvements learned from 18 months of operating experience. The new furnace featured automatic electrode positioning, improved refractory design, and power control systems that reduced electrical consumption while increasing melting speed. Installation of the second furnace required additional electrical infrastructure that strained Syracuse's power grid beyond original projections. Niagara Mohawk engineers calculated that 2 furnaces operating simultaneously would consume 1,800 kilowatts, nearly double the original estimate. Additional transmission lines and transformer capacity cost $38,000, but the investment enabled Halcom Steel to operate both furnaces continuously, producing 4,000 pounds of steel every 3 hours. Annual production reached 5,000 tons by December 1907, rivaling established Sheffield producers who had dominated tool steel markets for more than a century. The tonnage represented remarkable achievement for a company that had existed less than 4 years. More significantly, quality control records showed consistency that exceeded Sheffield Steel. 97% of Halcom Steel's production met or exceeded customer specifications, compared to 85% for imported Crucible steel. The success created unexpected challenges that Crucible producers had never faced. Steelworkers' unions demanded wage increases for operating dangerous electric equipment, citing electrical shock risks and arc flash hazards that did not exist with coal-fired Crucible furnaces. Union representatives argued that electric furnace operators deserved premium pay for mastering complex electrical controls and high-voltage systems. Halcom agreed to 15% wage increases while implementing comprehensive safety training programs that reduced electrical accidents to 0. Insurance companies tripled premiums after learning about electric arc operations, claiming that electrical furnaces presented explosion risks from arc flash incidents and power system failures. Underwriters demanded detailed engineering reports proving that electric furnaces operated safely under all conditions. The insurance requirements forced Halcom to document every aspect of furnace design, electrical systems, and operating procedures, creating the first comprehensive electric arc furnace safety manual in American industry. The most threatening challenge emerged from Crucible Steel's legal department. Former board members filed patent litigation claiming that Halcom had stolen proprietary metallurgical secrets when he resigned as president. The lawsuit alleged that Keto Steel compositions violated Crucible's trade secrets and that Halcom's recruitment of metallurgists constituted unfair competition. Legal fees consumed $25,000 during 1907 while threatening to disrupt customer relationships and supplier agreements. Patent attorneys argued that electric arc technology represented fundamental innovation rather than theft of Crucible methods. The electrical heating process, electrode positioning systems, and power control mechanisms bore no resemblance to Crucible technology. Most importantly, Keto Steel's superior performance resulted from metallurgical control that Crucible methods could not achieve, proving that electric furnace technology created genuinely new capabilities rather than copying existing processes. The litigation revealed Crucible Steel's growing concern about electric arc competition. Internal correspondence disclosed during discovery proceedings showed Crucible executives tracking Halcom Steel's production increases, customer acquisitions, and technical innovations. Crucible's board discussed acquiring electric furnace technology, but rejected the investment, believing that crucible methods would remain dominant. Their lawsuit represented desperate attempts to prevent technology they had refused to adopt from destroying their market position. By December 1907, Halcom Steel operated 2 electric furnaces producing 8,000 tons annually, while maintaining quality standards that exceeded Sheffield Crucible Steel. Customer orders backed up to 8 months, with major manufacturers willing to wait for keto steel rather than accept available crucible steel alternatives. The American tool steel industry had achieved technological leadership that European experts had declared impossible, proving that electric arc innovation could surpass centuries of established tradition. The electrical storm struck Syracuse at 11:27 on the morning of October 15, 1908, with lightning that severed Halcom Steel's dedicated power lines, just as 2,000 pounds of molten steel reached 3,200 degrees in the primary electric furnace. The sudden power loss killed the electrical arcs instantly, leaving superheated steel to cool and solidify inside the furnace chamber, while Halcom watched helplessly from the control room. Within 30 minutes, the molten steel had frozen into a solid mass that cracked the refractory lining and rendered the furnace inoperable. The damage assessment revealed catastrophic failure that crucible methods had never experienced. The frozen steel mass weighed nearly a ton and filled the entire furnace chamber, making removal impossible without dismantling the refractory structure. Specialty contractors quoted $30,000 for complete furnace reconstruction, including new refractory bricks, electrode systems, and power connections. The repair timeline stretched to 6 weeks, during which Halcom Steel could not fulfill any customer orders or generate revenue to meet payroll obligations. Financial pressures compounded the technical disaster with brutal timing. The 1807 bankers' panic had disrupted capital markets nationwide, forcing banks to restrict lending and call existing loans to preserve liquidity. Onondaga National Bank, which had financed Halcom Steel's expansion, faced its own survival crisis and demanded immediate payment of $150,000 in outstanding loans. The bank president delivered the ultimatum personally: full payment within 30 days or foreclosure proceedings would begin on October 20th. Halcom's personal financial situation offered no relief. He had mortgaged his family home to secure expansion loans, invested his entire savings in company stock, and pledged future profits against equipment purchases. The frozen furnace disaster eliminated revenue while accelerating cash requirements for repairs and loan payments. His accountant calculated that Halcom Steel owed $200,000 with liquid assets totaling less than $25,000. The technical implications threatened electric arc technology's fundamental credibility. Crucible Steel's lawyers filed emergency motions citing the frozen furnace incident as proof that electric furnaces were inherently unreliable compared to crucible methods. Coal-fired crucible furnaces could be interrupted safely, then restarted when fuel supplies resumed. Electric furnaces failed catastrophically when power disappeared, destroying equipment and contaminating steel charges. The legal arguments resonated with customers who demanded supply reliability above technological innovation. Major customers canceled orders within days of learning about the frozen furnace disaster. Pratt & Whitney, which had contracted for 6 months of keto steel deliveries, terminated their agreement citing supply reliability concerns and force majeure clauses that excused performance during equipment failures. Brown & Sharp followed immediately, then Cincinnati Milling Machine Company. 6 months of backlogged orders worth $300,000 evaporated in 2 weeks of customer defections. Local newspapers sensationalized the electric furnace failure with headlines that declared Sheffield methods vindicated. The Syracuse Herald published detailed articles explaining why European steel masters had correctly predicted American electric arc experiments would fail. Editorial writers characterized the frozen furnace incident as proof that industrial innovation required decades of development rather than reckless experimentation. The Syracuse Post-Standard quoted unnamed Crucible Steel executives claiming that electric furnace technology was fundamentally flawed and commercially unsustainable. Employment at Halcom Steel collapsed from 200 workers to 45 within 3 weeks. Skilled metallurgists returned to Crucible Steel, which welcomed former employees with salary increases and public statements about the wisdom of traditional methods. Furnace operators, electricians, and maintenance workers found positions with conventional steel companies that operated reliable crucible furnaces. The exodus of experienced personnel eliminated institutional knowledge about electric arc operations that had taken 4 years to develop. Personal costs mounted as Halcom exhausted every financial resource to maintain operations. He sold his stock investments, mortgaged life insurance policies, and borrowed against his wife Sarah's inheritance to meet payroll obligations. Sarah pleaded with him to accept Crucible Steel's offer to return as vice president, arguing that his family's security mattered more than proving electric furnace technology. The offer included full salary restoration, stock options, and guaranteed employment despite the competitive conflict his independent company had created. European steelmasters interpreted the frozen furnace disaster as definitive proof that American electric arc experiments had failed. The London Iron and Coal Trade Review published detailed technical analysis explaining why electric furnaces could never achieve the reliability of crucible methods. Sheffield steel companies increased marketing efforts in American markets, emphasizing their century-plus track record of consistent quality and reliable delivery. Orders for imported crucible steel increased 30% during the fourth quarter of 1908. The cascading failures revealed electric furnace technology's Achilles heel: complete dependence on electrical infrastructure that could fail without warning. Crucible furnaces operated independently, requiring only coal and skilled labor to produce steel consistently. Electric furnaces demanded reliable power generation, transmission systems, and electrical controls that could malfunction simultaneously. The October storm had demonstrated that a single infrastructure failure could destroy months of production and eliminate customer confidence permanently. By December 19, 2008, Halcom Steel faced immediate bankruptcy with debts exceeding assets by more than $100,000. The damaged furnace remained inoperable while legal costs from patent litigation and loan defaults consumed the last available cash. Halcom's personal net worth had evaporated along with his company's prospects, leaving him financially ruined and professionally discredited. The man who had revolutionized American steel production 4 years earlier now faced the choice between personal bankruptcy and complete capitulation to Crucible steel tradition. The technical failure that destroyed Halcom's fortune contained the seeds of ultimate triumph, though neither he nor his critics recognized the opportunity hidden within catastrophe. The frozen furnace incident had revealed electric arc technology's vulnerability, while simultaneously demonstrating the path toward permanent solution. Power interruption caused catastrophic failure, but power interruption could be prevented through engineering innovation that would make electric furnaces more reliable than crucible methods rather than less reliable. The darkest moment of Halcom's career approached as 1908 ended with legal notices demanding payment of debts that exceeded his remaining assets. American tool steel production appeared destined to remain forever subordinate to Sheffield supremacy, while electric arc technology seemed relegated to experimental curiosity rather than industrial revolution. The frozen furnace that had cost Halcom everything would ultimately teach him how to create steel production methods that time itself could not defeat. The revelation struck Halcom on January 3, 1909, while staring at the frozen mass of steel that had destroyed his company's future. The power interruption was not evidence of electric furnace failure, it was proof that electric furnace technology had not yet achieved its potential. Crucible methods succeeded because they operated independently of external systems, but electric furnaces could surpass that independence by eliminating the possibility of power failure through redundant electrical systems and controlled shutdown protocols. Working 18-hour days in his damaged facility, Halcom collaborated with General Electric engineers to design backup power systems that would prevent catastrophic furnace failures during electrical storms. The solution required massive motor generator sets, essentially electrical batteries weighing 12 tons each, that could maintain furnace power for 30 minutes during grid interruptions. The motor generators would spin continuously during normal operations, storing kinetic energy that converted instantly to electrical power when primary service failed. The engineering breakthrough emerged from studying the frozen steel disaster. in metallurgical detail. Chemical analysis revealed that rapid cooling had created microscopic stress fractures throughout the solidified mass, but controlled cooling could prevent those fractures while achieving superior grain structure. Halcom developed controlled cooling protocols that safely shut down electric furnaces during power interruptions, gradually reducing temperature over 6 hours to prevent thermal shock and refractory damage. The financial salvation arrived unexpectedly on February 27, 1909, when Andrew Carnegie's private railroad car stopped at Syracuse Station during his inspection tour of American industrial facilities. Carnegie had heard rumors about electric arc steel production and demanded personal demonstration of the technology that European experts claimed was impossible. Despite the damaged furnace, Halcom presented detailed metallurgical data proving electric steel's superiority over crucible methods. Carnegie studied the chemical analyses with the expertise of someone who had built America's largest steel empire through technical innovation rather than financial manipulation. The carbon content uniformity, inclusion counts, and mechanical properties exceeded anything Carnegie had achieved with conventional furnaces during 40 years of steel production. After 3 hours of technical discussion, Carnegie provided $250,000 in funding, declaring Halcom's process the future of specialty steel production in America. The investment enabled complete facility reconstruction with improvements that eliminated every weakness revealed by the October disaster. Halcom installed 2 backup power systems, the motor generator sets for immediate response, and a steam-powered electrical generator for extended outages. The new furnace featured improved refractory design using magnesite bricks that could withstand repeated thermal cycling without cracking. Most importantly, the controlled cooling systems allowed safe shutdown and restart without equipment damage or steel contamination. Construction of the rebuilt facility attracted national attention from metallurgical engineers who had dismissed electric arc technology after the frozen furnace incident. The backup power systems, controlled cooling protocols, and improved furnace design addressed every criticism that crucible advocates had raised about electric furnace reliability. Technical journals published detailed articles describing Halcom's innovations as potential solutions to problems that had plagued electric furnace development since Héroux's original invention. Production resumed in August 1909 with capabilities that exceeded the original facility's performance. The improved furnace melted 2,000 pounds of steel in 75 minutes while maintaining temperature control within 5 degrees Fahrenheit throughout the heating cycle. The controlled cooling systems enabled 24-hour operations by allowing furnace shutdown and restart without equipment damage. Annual production capacity reached 15,000 tons, more than many established Sheffield companies achieved with dozens of crucible furnaces. The technical validation came through rigorous testing that surpassed all previous steel quality measurements. Watertown Arsenal conducted comprehensive analysis comparing Halcom's rebuilt facility's output against the finest Sheffield crucible steel available in American markets. Every measurement favored electric arc steel. Hardness, uniformity improved 20%, inclusion counts dropped 40%, and edge retention increased 60% compared to crucible steel from the same raw materials. Customer confidence returned gradually as Halcom demonstrated reliable production through the winter of 1909. Brown and Sharp renewed their Quito steel contracts after witnessing continuous furnace operations during electrical storms that would have interrupted crucible production. Cincinnati Milling Machine Company placed orders worth $50,000, specifying electric arc steel for cutting tools used in locomotive manufacturing. Most significantly, the United States Navy requested samples for evaluation in armor-piercing projectile applications. The Navy testing protocols exceeded civilian standards, subjecting steel samples to stress conditions that would destroy inferior materials. Blind testing compared Sheffield crucible steel against Halcom's electric arc steel in projectiles designed to penetrate battleship armor plating. The results revealed American steel's decisive superiority: 25% better penetration performance and 60% fewer stress fractures during high-velocity impact testing. The $2 million Navy contract awarded to Halcom Steel in December 1910 represented more than financial success. It constituted official recognition that American electric arc technology had surpassed European crucible methods in the most demanding applications. Navy metallurgists specified Halcom steel for submarine hull components, destroyer propeller shafts, and battleship gun barrels where material failure could cost lives during combat operations. The ultimate vindication arrived in September 1911 when Crucible Steel Company approached Halcom with an acquisition offer that acknowledged electric arc superiority. The company that had rejected his electric furnace proposals 8 years earlier now recognized that crucible methods could not compete with properly engineered electric arc technology. The acquisition price of $1,500,000 represented 7 times Halcom's original investment, but more importantly, it merged his innovations with America's largest tool steel production capacity. The consolidated Sanderson-Halcom works combined crucible steel tradition with electric arc innovation under Halcom's technical leadership as chief metallurgist. By 1920, Crucible Steel operated 12 electric arc furnaces producing 100,000 tons annually while maintaining the quality standards that Halcom had established during his independent operations. The controlled cooling protocols, backup power systems, and improved refractory designs became industry standards adopted by electric furnace operators nationwide. The wartime expansion during the 1940s elevated electric arc steel production to unprecedented sophistication. Crucible Steel developed vacuum arc remelting technology that combined Halcom's electric heating principles with atmospheric control impossible during his pioneering work. Tools made with this refined process in 1943 achieved metallurgical perfection through controlled heat treatment at 1475 degrees Fahrenheit, vacuum remelting at 0.1 torr pressure, and slow cooling over 72 hours. The molecular structure that resulted from Halcom's electric arc innovations, refined through 4 decades of development, created tools that outlasted generations of use. A 1943 Crucible steel chisel forged with technology that traced directly to Halcom's 1906 breakthrough, maintained its cutting edge through 80 years of continuous service because American ingenuity had finally surpassed Sheffield steel through electrical innovation that European experts had declared impossible.